Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to take a look at what are called the, this is section 4.4 in our text, and we'll probably do this in a few parts. And the first part is called the orthonormal basis. So, and I'm going to just write that as capital O, capital N from here on out, because that's a lot to write otherwise. So, what is an orthonormal basis? So here's what we say. We say let Q1, Q2, up to Qn be let's just write that. Let those be an orthonormal, ON, an orthonormal basis for Rn. Then the following is true. Actually, it's more than one, so it's the following are true. All right, well, let's see what we have that are true. Following are true. Here we go. 1. What it means, and let me just say what this means. It means two things. First, all Qi are orthogonal to each other, are orthogonal to each other. And secondly, each vector has a length of 1. Okay, and we're going to take a look at a few examples. We'll see why that's so important. But let's write this out. So the first thing that you would informally say is you would say that Qi times, or transpose, times some Qj equals 0. Well, when does it equal 0? If these are orthogonal vectors, it means that it equals 0 when they're different vectors. Oops, oh, I have I. That really should be I at j. Let's fix that. Ij equals 0, and it equals 0 when I and j are different letters, and we'll see that too. 2, it says that if you take Qi transpose with some Qj and you get Qj, that gives you 1. Well, that gives you 1 when we already said if they're different you get 0, so it gives you 1 when they're the same, when I equals j. For example, so let's do that. For example, Q1 transposed Q1 equals 1, while Q1 transposed with Q2 would be 0. Okay? And then the last and third condition we have 3. 3 says that the length, let's write it this way. It says that the length of any Qi is equal to 1, which is also the same as saying that the length of Qi squared is also 1. So we'll use those interchangeably as we need them. So let's take a look at how this is going to begin to help us, especially in the light of many of the things that we've learned. So let's try this. For example, recently we were solving this problem A transpose A x hat equals A transpose B. Okay, well, this is our recent studies, the projections recently, but what about if A equals Q. Well, let's see what happens. Well, this just gets written in as Q transpose Q. X hat equals Q transposed times B. All right, well, let's take a look at what does Q transpose Q give us. So let's write it this way. The first matrix of Q transpose is going to be, remember, it's going to be Q1 transposed, Q2 transposed. You could go all the way out to Qn. I'm just going to go, we'll just take a look at Q3. I think you'll see the pattern at that point. Times the matrix of Q, well, that has columns of Q1, Q2, Q3. Well, let's think about what this means. This is an inner product. Well, this is going to give me the matrix of, so it's going to be the row 1, so it's Q1 transpose times Q1. So this is Q1 transpose Q1. Then we're going to get in the row 1, column 2, we're going to have a Q1 transpose Q2. And then we're going to have a Q1 transpose Q3. Okay, and then let's go to the next row. That's going to be Q2 transposed Q1, Q2 transposed Q2, and finally Q2 transposed Q3. And then our last row, we're going to have a Q3 transposed Q1, Q3 transposed Q2, and finally we'll have a Q3 transposed Q3. Okay, well let's see what this gives us. Well, notice, this is worth noting, so let's grab a few colors to note these things. First off, here I is equal to j, I is equal to j, 1 is equal to 1. So in other words, if we, according to rule number 1, I'll put it also in a blue box. Well, I'll put it in the blue box, the correct blue box. Let me fix my blue boxes there. So the correct blue box says when those match that this is just 1. Well, look at how many blue boxes I have. That's 1 also, and so is Q transpose Q3. Those are all blue boxes. Those are all 1. Now let's take a look at red boxes. Well, what happens in the red boxes? Well, for example, here's one that says Q1 transpose Q2. In this case, 1 is clearly not the same as 2. Well, that goes back to rule number 1. So in other words, all of my red boxes, all of these become 0. All of these where the indices do not match become 0. Well, what do we have? What do we have? Let's see. In other words, this just gives me that's the 3 by 3 identity matrix. As a matter of fact, that's what Q equals. Even if Q is not square, Q transpose Q still gives you the identity matrix. Okay, let's see, what else do we want to do with that? I wanted to... Let's take a look at an example now. Let's take a look at an example. So I'm going to leave this information. Yeah, let's do this. Let's leave this information. No, let's do this. So what about solving our problem now? So let's go solve our problem. And our problem probably needs a new page. So let's go to a new page and let's solve our problem. So remember, this whole problem started out as A transpose AX hat equals A transposed B. Well, now we said, well, what if we have an orthonormal basis for A? So we have Q transpose Q X hat equals Q transposed B. Oops. Q transposed B. Now, Q transpose Q, we just said that's the identity. So in other words, X hat is very simply Q transposed B. All right, well, then remember what we said. Originally, solving our first equation then, we said then that the projection P is A times X hat. Well, now we have that, and I should put this, let's try this, let A equal Q. Well, now what do I have? So P is, well, A is a Q. X hat we've solved, that's Q transposed B. Wow. Let's expand it. Let's see if we can expand Q times Q transpose times B. So here we go. Q times Q transpose. Well, Q is the matrix with columns. We'll just use a 3 by 3 for now. 1, Q2, Q3 times Q transpose. Well, that's going to be Q1 transposed, Q2 transposed, and finally Q3 transposed times transposed, oh goodness, yeah, transposed times the vector B, and I'm just going to write it as the vector B. So let's do some associative properties here. I'm going to start here with, those are actually a bracket, not a matrix now, even though it will be. So let's see. So I'm going to leave my first matrix untouched. So Q1, Q2, Q3 times, well, think about this. This is a row times a column, and that's just some number. That's just a number. So let's write that as Q1 transposed B, Q2 transposed B, and finally we have Q3, be careful, I'm at the bottom of my screen, B. Now remember, each of those is just the component of this column vector. Well, wait a minute, we know what this is. This is the matrix Q times a column vector. In other words, these elements of this vector are just the weights of the linear combination of the columns of Q. All right, that's a lot. That's the weights of the linear combination of the columns of the matrix Q. Well, let's write that. Let's write that and see what happens. So what am I at? This is my P. I'm going to bring P down because we're going to have to carry this over here. So now I have that P is equal to, well, this is going to be, we're going to write it this way. We're going to write it as Q1 times the weight of Q1 transposed B plus Q2 times Q2 transposed B plus Q3 times Q3 transposed B. That's the projection. Now we've solved all of our problems. Well, but we can even go one step further. Suppose this. Suppose Q is a square. Or you could say is n by n. Well, if the columns of Q form a basis, that means all the columns of Q are linearly independent. That means that if you were to row reduce Q, you would end up with, or take Q to R would just give you the identity matrix. So in other words, you have a full rank matrix. Or in other words, QX equals B always has a solution. Has a solution because it has n independent columns with rank n. Right, so what does that mean? That means that if you have a projection P onto the column space of Q, that means that P is in the column space. In other words, P is B. So that's the big takeaway. This here implies then that P equals B. So wait a minute. Now I can rewrite this equation that I'm going to point to in red. We can rewrite this equation. We can rewrite this equation then as B. Some vector B is equal to Q1 times Q1 transposed B plus Q2 times Q2 transposed B plus Q3 times Q3 transposed B. And it's at this point that this result is bigger than it may appear. And so I'm going to try to explain it, and then we're going to show it. And I'm going to show it in 2 examples. But look at what this means. This means that B is now a linear combination of the Q's. It's done for us. We already know what the answer is going to look like. It's already done for us. So let's see how this works. I'm going to copy let's see if I can do this correctly here. I'm going to copy my B. Copy. We're going to go to this page here. And let's tap. Well, that didn't work, but that's okay. We can easily fix that. Here's how I'm going to fix it. I'm just going to write it. So B is equal to Q1 transposed B plus Q2 transposed B plus Q3 times Q3 transposed B. All right, let's take a look at an example that would help us to see what this means. So example. And we're going to learn a bit more too. This is a good example. Let A be the matrix of 1, 2, minus 2, 1. Okay? Now notice this. So I'm going to say, let's call this, it has columns of A1 and a column of A2. So those are my columns that I have. Well, let's try this. What happens if I take A1 transposed A2? Well, this is just going to be the 1. I'll write it out. 1, 2 times the column. So A transpose times minus 2, 1. And you can see that this equals 0. So what does that mean? That means that A1 is orthogonal to A2. However, so not only are they orthogonal, they're linearly independent, and they are going to be we have a full rank matrix. So any projection onto the column space will have a solution. But I want to go a little bit further then. So we've said that the columns of A are orthogonal. I'm going to put this, but A1 and A2 are not. They are not orthonormal. Orthonormal. I should have written ON. Norm are not orthonormal. So here's how we would make them orthonormal. So what we have to do is make them of length 1. And to make them length 1, well, so I'm going to call A1 will become Q1, meaning it's orthonormal. If we take A1 and we divide it by its length. And we have to do the same to get a Q2, we have to take the second, that's A2, and we have to divide it by its length, A2. Okay, so let's find that. So the length of A1 is the square root of 1 squared plus 2 squared. Well, that's just the square root of 5. And you can see, or should verify, this is also the length of A2. So now I can write the matrix Q. So let's write that. So in other words, the matrix Q means that everything just gets multiplied by 1 over the square root of 5 times the matrix A. 1, 2, minus 2, 1. So you could write it like that, or if you wanted, you could write it as 1 divided by root 5, 2 divided by root 5, minus 2 divided by root 5, and 1 divided by square root of 5. Okay, so you can write that either way. Okay, now let's do this. Let's just take some vector. Let's just take a vector and let's multiply it. So let's try this. Let the b equal the vector 0, 2. B is the vector 0, 2. So what I want to do is find a couple things. Let's find the length of b. And then we're going to find a times, we don't want b to be 0. We want x, sorry, not b. We'll do that. Let b equals 0, 2. So we're going to do a few things. We're going to find a times b, and then we're also going to find q times b. All right, let's try these things. The first thing is this. The length of b, I'm going to just write it as the length squared. It doesn't really matter. That way I don't have to have a square root. So the length of b is just 0 squared plus 2 squared. That's just 4. Okay, now let's take, and then we're going to find the length. You know what? Let's write it this way. Not just AB. That's not interesting. How about the length of AB? And then we're going to find the length of Q times B. Okay, there's a lot to do in this problem. So let's try this. The length of A times B. Well, first, we have to find what A times B is. So let's do that. 1, 2. Minus 2 times 1 times 0, 2. Well, that's going to give us a minus 4, 2. Okay. And so we could say that the length of A times B, well, that is equal to negative 4 squared, that's 16, plus 2 squared, that's 4. So the length of AB squared is 20, or you could say that the length of AB is the square root of 20. Let's try again. So now let's find Q. Q times B. All right, so let's just write this out. This is 1 divided by the square root of 5, 2 divided by square root of 5, minus 2 divided by the square root of 5, and then 1 divided by the square root of 5, times the vector b, which is 0, 2. Okay. So that's going to give me 0. This is going to give me a minus 4 over root 5, and it's going to give me a 2 over the square root of 5. Well, now let's find the length. So then the length of Q times B, we'll just do it squared. Well, I'm going to take a negative 4, and I'm going to square it. That's 16, divided by the square root of 5 squared, plus 2 squared, that's 4, divided by the square root of 5 squared, that's 5. This is 20 over 5, that's just 4. But wait a minute, that's the same as the length of B. And the question is, coincidence? Let's check. Let's try this. So let's find the length of any vector, just q times x in general. Well, let's think about this. What we don't know is that the length of x is difficult to find. So let's try this. What about the length of qx squared? Well, remember what that came from. Remember that q times x is a vector. So in other words, this is the same as the vector of qx transposed qx. But our properties tell us that this is the same as x transposed q transposed times q times x. Well, what is q transpose q? That, okay, here we go. Let's turn the screen down for a moment. Q transpose q, and let's go to see if I can dig that up. Q transpose q, what did we get? Oh, there it is. Q transpose q is right here. I didn't maybe make it clear enough. I didn't make it clear enough. That's right here. There is q transposed q, and we said that it just equals the identity. So now we're ready. If we come back here, our final result just says that this is equal to x transposed I x, but this is just x transposed x. The big takeaway is then that when you have an orthonormal matrix and you multiply it by a vector, it doesn't even change the length of the vector. It doesn't change the length of the vector. Okay, we're going to do one more with this, one more example with this. Or we're going to continue this example, and that is we're going to go to another screen, and we're going to write b, which we said is 0, 2 as q1 transposed b plus q2 times q2 transposed b. And remember that this is just an R2, so there's only going to be q1 and q2, which we have found. So let's do this. Okay. I want to draw this because it's actually worth seeing, and that might, I think, help us. So let's do that. So I'm just going to sketch this picture here. Now, put some tick marks. 1, 2, maybe 3. 1, 2, 3. Let's go 1, 2, 3, maybe 1, 2. So let's draw in, and maybe we'll use this pretty gold color. So the vector A1, is right here. So I'm going to just make a line like that. And we have the vector Q2, or A2. A2 is probably about there. Okay, so this is A2, this is A1. Now, what is important here is not just that, but remember that Q1 and Q2 were scaled down versions of these. And so I'm going to grab a calculator here, and let's just take and, for example, divide by the square root of 5, and we'll see what we get. So if I take 1 and I divide it by the square root of 5, I get 0.44. Okay, so 1 divided, so Q1 is really this vector here. It's this little vector there. And Q2 is going to be, about there, is going to be this vector here. They were just scaled down, but again, you can see that they are perpendicular, and the graph's just trying to show that. So there's my Q2, there's my Q1. Now, the vector that we were looking at today was this blue vector. This blue vector here, that was the vector 0, 2. Now, let's try this. Let's see. So let's find each one of our parts. Okay. So let's try Q1 transposed B. Okay, here we go. Q1 transposed B is going to be, so Q1 is 1 over the square root of 5, 2 over the square root of 5, times the vector, oops, I wrote that in the wrong way. That's a transpose. Let me correct that. It's 1 divided by the square root of 5, 2 divided by the square root of 5 times the vector b, which is 0, 2. Well, look at what that gives me. That just gives me the scalar of 2 times 2, that's 4, of 4 over square root of 5. So my first component then, is Q1 times Q1 transposed B was 1 divided by square root of 5, 2 divided by the square root of 5, times 4 divided by the square root of 5. Let's factor this. Let's factor, how about a root 5 out of there? So that just leaves me back with A1, the 1, 2, times, now we have the scalar of 4/5. Okay, now let's do this again, scalar of 4/5. Let's do this again for the Q2 components. So let's start with Q2 transposed B. Well, Q2 is minus 2, so minus 2 over root 5, and then up 1 root 5 times B, which is 0, 2. Well, this is going to give me 2 over the square root of 5. So now I can write Q2 times Q2 transposed B, which is equal to minus 2 square root of 5, 1 divided by root 5, times 2 divided by root 5. I'm going to factor out a root 5. What the heck? Let's see, that's going to give me a minus 2, 1, times this scalar of 2/5. 2/5. Well, there we have it. We just did it. So B now is equal to, this. We can see this. I like how this is working out. This is the first vectors, Q1 transpose B is the scalar of, I'll write it this way, 1, 2 times 4/5 plus the Q2 components are going to be minus 2, 1 times 2/5. Well, let's see where that is. Let's kind of look at our graph. I wish I had like a perfect scale. I don't, but if we do this in green, I think it'll become pretty apparent. The Q1 components are just the 4/5 of the vector 1, 2. Well, 4/5 of 1 is probably right about there. And that gives me the 4/5 of 2. And look at that. It comes right back to an orthogonal projection onto our first basis vector, or the line defined by it. And if we look at our other one, maybe in this pretty pink color, we'll see that the Q2s, we take 2/5. So example, 2/5 of 1 is not very far out, is it? It's maybe there. And so what is this going to give us? It's going to give us something, the scale's a little off, but it's going to give us this projection. And so there it is. You can see that now the vector B has been written in terms of its orthonormal basis and some scalars as a simple linear combination. And we're going to stop this video at this point. In the next video, we're going to take a look at one more famous example, the rotation matrix. And then we're going to be looking at, well, if these orthonormal bases are so important, how can I get one? I hope that helps. Thanks for watching.